This is the second lecture on using the Go programming language to determine a Mars transfer orbit. This will focus on the physics involved that we need to know to solve this problem. If you haven't done so, you should probably go back and watch the first lecture before you go through this one. Okay, so let's talk about some basic physics. There really are only two equations we have to know, and neither of which are really all that complicated. The right way to think of them is that they're first principles in science. They're just the way nature is, and they represent how forces act in the universe. So, Newton's law of universal gravitation was discovered by Isaac Newton, and the idea is how to represent the way gravity works. So the basic idea is that any two bodies with mass in the universe are attracted to each other. So, for example, I have this blue one on the left here, and it might have mass 1, and I have a blue one on the right, it might have mass 2. And what Newton said, which turns out to be correct, is that they are mutually attracted to each other, so they feel a force. This body over here, mass 2, feels a force pulling it towards the first body, and the force that it feels is given by an expression that depends on the two masses, and specifically I wrote them next to each other. That's m1 times m2, the product of the two masses. It also depends on how far apart they are. Specifically, it depends on how far apart they are squared, so that r is the distance between the two bodies. So if I move farther away, the force gets smaller. And by this way, an important thing to think about in terms of sort of physics is the fact that it's squared. So if you don't quite follow this right now, don't worry about it too much, but if I move something to be twice as far away, so this r term becomes twice as big. If I square something twice as big, the 2 part of twice as big gets squared, so it's 4 times bigger. And that's in the denominator. So if I move something twice as far away, the force it feels is 1/4 what it was before. And finally, it's not just exactly the product of the two masses divided by r squared. There's some constant that gives us how big that force is. So this whole expression, if I know the masses, the distance between two things, I know the gravitational force that exists between them. And this is a universal law of gravitation. So, one way to think of it in terms of the planets is the Earth is subjected to a force pointing towards the Sun. Corresponding, the Sun feels a force pointing towards the Earth. This force, one way to simplistically think about it is if there were no gravitational force, the Earth would just keep traveling in a straight line, whatever direction and whatever speed it's moving in. But what this force does is it causes it to follow its orbit. Right, some important numerical values that we need to know. The first is this universal gravitational constant is given by this number here, 6.67408 times 10 to the minus 11 power. So I'm going to zoom in for a second here. I didn't write its units because the units are actually kind of complicated. They are meters cubed divided by kilograms seconds squared. That's quite a small number. 6.67 times 10 to the minus 11th. So if I just write it as 6.6, I need to move the decimal point 11 places over here. So it's 0.000, a lot of zeros, 667408. So it's a very small number. So we're going to try to go to Mars, and so the bodies that are important in this problem are the Sun. Everything is orbiting the Sun, and most of the time when our spaceship is going between the Earth and Mars, its main influence will be the Sun. It'll orbit the Earth, so I need that mass. It'll orbit Mars, so I need that. This is in a way just a made-up thing because I don't know what the mass of the spaceship going to Mars will be. Will probably actually be smaller than this, but I'm just going to use the mass of the space station for our particular problem. We also need some other quantities. These three r's are different radii of different things. So r Earth is just the radius of the Earth. That's the distance from the center to the edge of the Earth. I have r Mars, which is that distance. I have a DSE. That means distance Sun to Earth. And I have d Sm, I believe, which should be the distance from the Sun to Mars. We need these quantities because when we're computing forces, we have to know the distances between them. Things will move, so those distances will change as it changes, but we need at least to initially set things up to have things correct. These two things we don't really need right now, but they're the velocity of the orbit of the Earth and the velocity of the orbit of Mars. So if you're ever wondering how fast the Earth is moving around the Sun, that's 29,800 meters per second. So that's the end of this lecture on how forces arise because of gravitational attraction between bodies, specifically in this problem, the Sun and the planets. The next lecture will focus on how the forces actually affect how things move.